Hello and welcome back to part 3 of our introduction to HPC at NC State. Today I'm going into a bit of a more in-depth overview of our HPC cluster, as well as the process for running applications using basic job scripts on HPC. So first, to kind of understand how job submission works on our cluster, you kind of need to understand the general structure of an HPC cluster. So a cluster is made up of something that you probably heard in the previous segments: nodes. A node is just a term for a computer or server that's part of a larger group. A cluster is made up of nodes. Our cluster, like most clusters at other universities, are made up of two broad types of nodes that there are subtypes within: login nodes and compute nodes. Login nodes are exposed to the internet. This is partly how you're able to log in, but it's also exposed to the file systems and the job scheduling system called LSF that is on our cluster. This means that from your login node, you can edit files, you can read and write, your scripts, and you can submit jobs to LSF, which is our job scheduler. However, login nodes are limited. There's only a few of them. They're not really designed for running large-scale compute tasks, and if everybody runs large compute tasks on login nodes, they'll shut down and nobody will be able to use them for anything. Compute nodes, on the other hand, can access those file systems and LSF, but they cannot access the broader internet, both incoming and outgoing traffic, meaning you can't download something from a compute node, and you also can't log into a compute node from an external source. You have to go through login nodes and really through this LSF job scheduler. Because of these differences, login nodes and compute nodes are used for different things, which is why this is kind of baked into our acceptable use policy. Login nodes are useful for tasks that either require internet access or don't take up a lot of computing resources. This includes things like navigating directories, editing text files or viewing text files, compiling code, installing packages, especially when that requires the internet, and anything else that requires access to the internet, like using wget or curl to download specific, files or databases, etc. Compute nodes then are used for everything else. Anything that requires a lot of computational power or a long time really to run, especially if it doesn't require any internet access or active monitoring, is what compute nodes are designed to do. And if you're using an HPC cluster, you're probably wanting to do tasks that require a lot of compute power, and so you'll probably mostly be using compute nodes for the actual computation you want to run. This structure fundamentally changes how you interact with something like an HPC compared to your own personal computer. So I like to use this little kind of analogy to think about what tasks make sense for my own personal computer or a workstation in my lab versus using an HPC cluster. I like to look at my personal computer, or this can be applied equally to a workstation, as like a personal kitchen. Personal computers and personal kitchens are multi-purpose. You can cook a lot of things in a kitchen, you can use your personal computer to do a lot of different diverse tasks, but they're also accessible. You can access these tasks at every step along the way, you can interrupt them whenever you want. They're generally easy to see and fairly interactive in an intuitive way. Personal computers and kitchens are perfect for a few tasks at a time. If you've ever been part of, cooking dinner for Thanksgiving, you know what it's like when your kitchen starts to have a few too many tasks to do at once, and it kind of strains the available space. But if you're just cooking, one particular dish, your personal kitchen probably has plenty of room to do it. And if you're just doing a few basic tasks, your personal computer is probably perfectly optimized to do that. However, both of these have limitations. If you're thinking about a personal kitchen, you have limited workspace. You could maybe cook something faster if you had, 2 or 3 extra people to help. But once you get up to more than that, your kitchen's likely going to run out of workable room. You might have a limited number of kitchen appliances. And there's also just limited storage space. You can only put so much stuff in your kitchen, or you can only have, so big of a pot. A kitchen is designed for everyday use, just as a personal computer is designed for everyday use. If your personal computer is like a personal kitchen, parallel computing, like an HPC cluster, is like a commercial kitchen or a food factory. These are designed for operating at scale. They have a large number of stations, they might have specialized equipment for cooking large amounts of food, and they're generally designed for many tasks to be executed at the same time without interfering with each other. However, because of this, they have slightly a different structure. They take in orders and produce outputs behind the scenes. This optimization for efficient work as opposed to accessible work does place some limitations. Like I said before, it has this kind of order placing structure rather than cooking it yourself and monitoring it yourself throughout the whole process. It's in general not designed for single discrete tasks. That's not what it's optimized for. It's optimized for a large number of tasks being run at the same time. This is how an HPC works. You don't monitor each task individually, like if you were working in RStudio on your personal computer. You submit a job script, like you were ordering something at a restaurant. The job scheduler, like the waiter, takes this job script back and distributes it to the chefs, which are the compute nodes. They all work in the background and produce outputs that you then check on later. This sort of structure means that HPC is not always faster than a modern PC, even though it has more compute power at its disposal. Part of this is that modern PCs and workstations have pretty powerful hardware. Like, each of their individual processors are fairly effective at running very quickly. There are certain compute tasks, even in research computing, that if they are running a series of tasks in a row, where each one depends on the previous task, might run faster on your own personal computer than on an HPC, even when they're set up. Aside from that, moving files to and from the cluster takes time. It doesn't take that much time once you're used to the tools, as you've seen from the previous segment, but it does take some time and some effort that isn't necessary if you already have the files where they need to be. Of course, this only matters if your workflow requires some other machine for pre-processing or data collection or something like that. You can often have workflows that exist entirely on the HPC, but if your workflow does require some other machine, moving files from that machine to the HPC may take time that makes the HPC end up not being a net positive in terms of efficiency. Third, an HPC cluster, particularly the compute nodes, is closed off from the internet. For certain applications that expect databases or websites or other external sources of data to be available as the job is running, this may require additional manual preparation, and sometimes requires digging into the documentation to find how to successfully point an application to local files instead of looking for them on the internet when the internet's not available. And finally, even if your script can run on the cluster and you navigate how to make it run without the internet, or it just simply doesn't need it, scripts and applications that are designed to run in a serial capacity, so just one step at a time, may need modification to actually take advantage of the available resources and run these tasks in parallel. This might mean, selecting specific options within an already written application that's designed to run either in serial or in parallel, or using wholly different, libraries or packages that are designed to take advantage of parallel architecture. So if you're thinking about moving your research workflow to HPC, think about whether you can answer yes to any of these questions. First is, does your workflow or your program or your application need more memory? This can be true for certain types of applications that don't necessarily need parallel computing power, like some specific large models in R, that run on a single core, but might need a lot of memory to store all the information as it's being, calculated and generated. If you run into that situation where your program is optimized as well as it can be, but it simply needs more memory, you might need to take advantage of something like an HPC cluster. Even if your research workflow could theoretically run on your machine, it's possible that it requires software that you either can't install or that's very complex to install on the either personal machine or workstation that you're running. In that case, if that software is already installed on the HPC cluster, either by HPC support or by other people in your lab or other collaborators, HPC might make sense. Third, if you need specialized hardware, which often means GPUs that aren't available on your machine, even if your workflow isn't a traditional HPC task, you might run it on the HPC to take advantage of those GPUs. That's technically a form of parallelized computing. You're running things in parallel if you're using a GPU, but it might not seem like the typical parallelization that you've heard of in other contexts. And finally, the classic use of HPC is if your program or your script repeats a large number of unconnected or loosely connected tasks. This is what HPC was designed originally for and is the most classic use of HPC. If you can take a specific computing task and turn it into a large number of unconnected or loosely connected tasks, this is a workflow that is ideally suited for running on the HPC cluster. So let's say, for the sake of argument, that you've reached the point where you know you want to use the HPC cluster for your research workflow. Or, on the other hand, you're just following this tutorial, you want to know how to use the HPC, and you'll figure out the workflow stuff later. These are the general steps that will be required essentially every time you submit a script for the HPC to process. I'm going to go over these steps in kind of a general sense first, and then I'll kind of break down each step individually. The first step is to create or modify your batch script. This is going to be a text file that contains the information necessary for the job scheduler to reserve the resources you need. as well as the actual lines of code that you're trying to run. Next, you will navigate to a job submission directory, which is just a location that is designed for rapid reading and writing, which is usually necessary during a job you're running on the cluster. This is usually going to be under /share/your primary group, and then your Unity ID, which will be found using these $group and $user variables. You will submit your job using bsub, followed by the less than sign and the name of that batch script that you have created or modified. As your job is running, you will check on the job progress using bjobs. This isn't, necessary every single time, but it's how you'll know whether it's still running or not. And then finally, you will examine the outputs, including the intended program outputs. You're probably running your job with the intent to make certain files, as well as the standard output, which is what your program prints when things go well, as well as the standard error, which is what your program prints when things go poorly. So the first step is that batch script. I will also use the word job script kind of interchangeably to batch script. The first line of a batch script, like any other shell script, always starts with a thing that's called a shebang line, because it starts with a hash symbol followed by an exclamation point. This will then be followed by the shell that you're going to be using to run all your commands. On our cluster, that will be /bin/bash. That's the location of the bash shell executable. This will be followed by a series of lines that start with bsub. These indicate that these lines are for the job scheduler, LSF, as opposed to being run directly in the shell. Every job script needs to include bsub-n, followed by the number of cores. For our purposes, we're going to be running serial jobs today, so the job is going to be 1, but you want to make sure that your job doesn't use more cores than you indicate with -n, or you can start running into issues with jobs not having the resources necessary because other people are using the other core. A batch script will always also include -w, and note that this -w is capital, followed by the max time to complete your job. This can be in seconds, minutes, and/or hours, up to a max time of 72 hours. This one you need to make sure is at least a little bit longer than the max amount of time your job will take to complete, because if you reach that wall time and your job isn't done, it will be shut down anyway. Now, the next 3 lines aren't required, but this is generally the minimum that you want to include for being able to keep track of what jobs you ran. This is especially useful when you come back to jobs later and you want to know what the heck was going on. So $J followed by the name of your job without any spaces. This is just some name that you can use to identify this job relative to others that might be running at the same time, followed by the location that you want to print your standard output to. That %J after it will be the job identification number, which is just, a series of digits that are used to identify that job from other jobs that are running, as well as the standard error, which can be printed to the same file as standard out if you like, but it's generally useful to print them to 2 different locations. Note that even if your job goes well, it will still print an empty standard error file if you indicate -e. Next, you'll run the lines to set up your environment, whether that's using environmental modules that have been maintained by the HPC staff, or something like a conda environment, or reading in certain config files, and then you'll actually run your program. Setting up your environment will sometimes, but not always, include modules that have been set up by the HPC staff. If you can use them, it can be nice, because then you don't have to worry about maintaining it yourself, but sometimes it'll conflict with what you're doing and you have to kind of create things yourself through something like conda. If you are planning on using environmental modules, these are some commands that might be useful. These commands include module list, which lists modules that are currently loaded. As you can see, I don't have any currently loaded. Module avail, which lists the available modules. This is going to be a giant list. You can scroll up and down using the arrow key. You can see that you have a number of modules that have the same name, but are different versions. For instance, you see under CUDA, we have things ranging from 7.5 up to 12.6. You can technically use grep to search for a specific module if you want to see whether they have it. For instance, if I want to grep CUDA, it should print out the lines that have the word CUDA in them. You can see there that it prints out those lines and highlights the word CUDA, so you can kind of navigate which ones are available, kind of search for whether a specific module is going to exist within our environmental modules. You can also load a specific module. You can see right here we'll do module load, let's say CUDA, and let's just leave it blank. If you just say module load CUDA, it will load the default version, which you can see from that printed screen before is CUDA 12.0. So if I say module list again, it shows CUDA 12.0. I can also use module unload to unload a specific module. For instance, if we use module unload CUDA and look at module list, now I don't have any module files currently loaded. If I load multiple modules, I'm going to clear all of them. Let's say module load CUDA, module load R, module list. You can see here that I have multiple modules loaded. If I do module purge and module list, now I don't have any module files loaded again. These modules most often are used to add a specific, directory to your path. For instance, right now, if I just have R, like I want to use R, nothing happens, right? I don't have R currently available. If I do echo path, none of these current locations have R in them. However, if I do module load R and type R, now it opens an R terminal, which I think I type quit to leave. And if I do echo path, you can see now that my very first thing in the path is this user local apps R bin. So that was the main thing that this module did, was add that to my path so that when I type in R, that's one of the places that my shell checks to see if that exists. One thing that I will note is that modules and things like Conda environments have a chance to conflict. For instance, if you install CUDA or CUDA dependencies or things that depend on CUDA in a Conda environment, and then load our HPC maintained CUDA module through module load CUDA, there's a good chance that one of the paths will kind of cross each other and make your whole thing get confused and error out. And so as a general rule of thumb, if you're using a Conda environment, install whatever dependencies you can, including something like CUDA, in the Conda environment whenever possible without involving environmental modules. One other example of this is R. If you're trying to run R in the HPC cluster, you technically can through module load R, but a lot of your specific packages will require libraries that you can't install without super user privileges, which you won't have on this HPC cluster because then you'd be able to erase other people's stuff. However, something like a Conda environment allows for workarounds like that, where you can install these libraries without requiring any special privileges. So in that case, if you're installing your R libraries and your R itself through Conda, you don't want to run module load R as well, because then your program is likely to call the wrong R environment when you type R later, or search for the wrong packages and libraries and that kind of thing. So the best way to understand these kind of steps is to try them out yourself. So right now we're going to work together to create or edit and submit a basic job script or batch script. So let's try this out ourselves together. First, we're going to copy over the tutorial folder from the user local apps samples guide folder into our home. We're going to use CP, which we're used to from that first segment, -R, recursive, which copies the whole contents of a folder instead of just a single file, /user, /local. Note that I'm tab completing some of these words. Good habit to get into. Apps, samples, and guide. And we're going to copy it to our home directory. Now if I ls my home and I grep for guide, you can see that it's in there. And if I cd home guide, I am in this folder. Now let's say I'm about to write this script. You might remember the lines from when I showed that example bash script. But for the sake of practice of how to do things when you're not really sure what to do next, we're going to practice navigating to the HPC documentation. So we're going to go to hpc.ncsu.edu. We're going to navigate to documentation and running jobs. And we're going to copy over this initial example for a serial job. This includes our shebang line, the -n line, the -w line, the -j, -o, and -e that I showed you from my example. So let's copy those lines over. Then we're going to use nano and create a new folder called guide submit.sh. This is a bash script, and the typical extension for a bash script is .sh, kind of like .txt at the end of a text file. Note that this isn't actually necessary for it to work properly. Linux doesn't really care how you do extensions. You can kind of write whatever you want. We could write, show and tell or something, and it would still work fine, but this is just so that other people know what this script is before actually looking at it. If they see the .sh, they know that it is a shell script, and specifically probably a bash script. So we're going to paste in those lines and edit them as needed. We only need one node for this because this is a serial script, and we are using bash, so we leave that the same. We're going to reduce this from 120 minutes to something like 10 minutes. We know that this is going to run pretty quickly. I'm going to rename this tutorial R, but you can call it whatever you want as long as you don't have any special characters or spaces. And we're going to leave these the same. Standard out %j and standard error %j. We're going to add a quick comment saying what this generally does. Batch script that submits simple R script. We're going to load environment, which we're going to use module load R. And then we're going to pause to slow job. We're going to use sleep, which is a command you may or may not know, which just pauses things for a little bit. It lets you do some testing to make sure, the job is being submitted as you want. So we're going to make it sleep for 20 seconds. You can make it sleep for a little bit longer if you want to make sure that you can get there in time. And then we're going to add a code to run our R script. Now, I have forgotten the name of this R script, and you might as well, so I'm going to quick exit out and then hop back in and enter the R script. So we're going to do Control X, Y, enter. Going to list the contents of guide, and I see this weather.r. So we're going to go back to the nano. We could copy and paste that if we wanted to, but I'm just going to go back to nano guide submit.sh. I'm going to run R script, which is the command to run a script through R. Home / guide / weather.r. I'm going to run Control X again, press Y, and click Enter to save. So now we've created our bash script. And if I run cat guide submit, you can see that this has been written and saved, and it's ready to be submitted. Now we are going to navigate to our job submission directory. This we're just going to use the base of /share, my group, and my user. If I do pwd, you can see that I am in my group, which is RFS, and my user, which is dmdefree. This means that any files that are automatically generated in your working directory, which for our purposes is going to just include the standard output and standard error, will appear in this scratch directory. If I do ls, you'll see that there are already a few things here. We're going to make a temporary directory for the purposes of this. Weather job. This isn't fully necessary for you, but it's just helpful for me to be able to see only the things that I'm looking for. And we're going to submit our job. So we're always running bsub, the less than symbol, which redirects your specific file to bsub as the input, and the batch script that we created, submit.sh. Note that your default memory is 2 GB per task, which translates to 2 GB per core that you reserve. Now, if I run bjob, so we only have 20 seconds to do it, you can see that my job is currently running in the debug queue, which is where typically small, fast jobs are going to run. It has a job ID of 82728 and a name of tutorial R. If I run bjobs again, it's no longer running. It's finished that 20-second test, and it's finished the job. So if you look in the folder that I'm currently in, you should see at least 2 output files. And you can see here that it's created a standard error file and a standard output file, as well as the weather.pdf file, which is the actual output of this job. If I do less to look at the standard output file. You can see some basic job stats, including where it was submitted from. Thankfully, it starts under share, which means that this job's going to operate at its maximum speed. And some general information for how effectively the job used its resources. You can note that it used a very, very small amount of memory, virtually zero, and that this is the script that was submitted. We check our error file to see if there are any errors. And you can see that there were no errors, which means it ran as expected. Also note here that this number, 82728, corresponds to what we saw under B jobs with the job ID. So if you ran the job again, it would have a new job ID, and so this standard output and standard error file would look the same except for this little job ID at the end. The weather.pdf file being created lets us know that this job kind of did what it wanted. If we want to take a little bit of a closer look, we can examine the file through something like Open on Demand. Back in our browser window, we go to serve.od.hpc.ncsu.edu, which is our Open on Demand location. Log in as necessary. And go to our files. And then let's say we navigate to /share/rfs, which is my group name, /dmd3, which is my user. Click this weather job and this weather PDF. And you can see that it's created, a little graph based on the R script that we ran. All of this tells us that our job ran as expected. It was successful. Great, we can move on. Now let's say instead of working successfully, like this one did, the job had an error at the beginning. Let's kind of simulate that really quick. We're going to, let's move this weather.pdf to a new file name, old weather.pdf, so we can make sure, whether or not this creates a new file. And let's make it somewhere else. That was a mess up. Now you can see that I have old weather.pdf instead of just weather.pdf. Now let's navigate back to our job. Vim, that's not right, nano, guide, submit.sh. Spelled that wrong. And we're going to make this R script, 2 R's. And this was from a testing earlier, don't worry about that. But let's say we mess up the name of the command. Now it's RR script instead of R script. That's not something that exists in our path, so it should give us an error. And we also have adjusted this sleep to be 10 seconds instead of 20, so I don't have to wait quite as long, because we kind of have a better sense of how to run B jobs. We use Control X to close, press Y to save, enter. And let's submit this job. B sub, less than sign, guide, submit.sh. We run B jobs. Note the new job ID number, 82756, and it's currently pending, so it's actually waiting a little bit for its resources. If we run it again, now it's running, excellent. It should finish in like 10 seconds. And now it's finished. If we look in this folder, we can see that we now have no weather.pdf, so it didn't run successfully. And we have 2 new files, standard output and standard error for this new 82756 job. If you weren't sure which one's newer and which one's older, you could use ls-ltr to organize, make it long form, organized by time, and in reverse. So that way the ones that are on the bottom are the newest ones. And your current directory. You can see that these 2 from this 82756 are newer than these ones. So let's say we want to take a specific look at our standard output to see what went right. You can see that we don't have any specific prints of something going correctly, which makes sense because the only thing that should have potentially printed something was this R script, which did not. And if we less the standard error to see what went wrong, RR script command not found. So it didn't produce the outputs we wanted, and it had an error file, which was in a separate file from the output file, which makes it a little bit easier to find instead of looking through what could be a very long standard output file from certain programs that print a lot. So our job has failed. Now we know it went wrong because I intentionally made it go wrong for the purposes of this exercise, but in a larger script with, let's say, tens, maybe even hundreds of lines, how do you debug when you have to submit and wait for responses to come back to you? It can get really, especially if you have to wait for a little while between each submission, it can become kind of frustrating doing all this debugging. Submitting multiple times, waiting for them to submit, and then checking the scripts. There is a solution. They're called interactive jobs, where you use LSF to open a shell on a compute node. So you can interact with it essentially like it was a login node, where you're writing specific lines in command line, seeing the responses, and kind of writing and debugging your scripts as you go. Please note, though, that even though this will feel more like a login node experience, you're still on a compute node, which means you have no access to the internet, so you can't download new dependencies or files that you need. However, if you have everything downloaded and you're just trying to make it work and get through some specific errors or bugs, an interactive job can be a useful way to do that. So to run an interactive job, we have this code right here, but since we're trying to do something and we aren't sure how, what is our first step? Navigating to the HPC documentation. So going to hpc.ncsu.edu, going down to documentation, and going to running jobs. We see here this basic batch script that we copied earlier. We also see options for an interactive job. Right here, it shows you bsub-is-n is 4, but that could be 1 just as easily. We don't need exclusive access to the node right now, and that kind of takes up resources other people could be using, but we'll copy this over just as a starting template. And we can paste it in here, get rid of this little -x, because we don't need exclusive access to this node. Other people can use it if they want to, because we don't think our job's going to take up a lot of memory, and we'll have 2 gigabytes reserved by default anyway. Click enter. And now we're on a whole new node. You can do echo hostname, which before would have been something like login03 or login whatever name you're on. In our case, now we're on this new node. And if you type htop, you can see that we're definitely not the only people using this node. A lot of other people are using a lot of different cores, but it looks like we have, it's currently using about 20 gigabytes of memory. There's about 188 available. We should be fine. Now, let's say we are trying to debug this script. We can print the contents of the script we're trying to run, guide submit.sh. We followed the same bsub-n and -w, so those should be the same. Just copy and paste the steps in our script. We know that it doesn't hit an error until here, but we're just going to do it one at a time for the purposes of testing. Copy, paste. That worked fine. Sleep 10. It's taking a second because it takes 10 seconds to run, because that's the point of that command, but it should run fine. And we run this -r script. We can see the command is not found. So he's trying to correct it once. And you think, okay, maybe it's not capitalized, just little R script. Still didn't quite run. That would have been a whole job submission process and checking the thing, but now we're doing an interactive job so we can just keep debugging. Capital R script. Runs as we expect it to. The little temperature is printed, null device, and if we ls, we see that we now have a weather.pdf. We click exit whenever we're done, and now we've left this compute node and we're back on login 03. And that just about wraps up what we're going to be covering today on basic job scripts on the Hazel cluster. If you'd like to check out the written documentation associated with running jobs, you can check it out at hpc.ncsu.edu/documents/lsf. I'd also recommend diving into parallel job scripts, which actually leverage the multiple cores and multiple nodes that can be found on the HPC cluster in our next video. Thanks and have a great day.